Welcome, space enthusiasts and curious minds. Today, we're diving into an astonishing revelation from the cosmos. The James Webb Telescope has just turned our understanding of the universe on its head, debunking many modern theories. In this video, we'll explore how this incredible instrument is reshaping our cosmic perspective. The James Webb Space Telescope has made groundbreaking discoveries that challenge the core principles of our contemporary understanding of the universe. This telescope has uncovered phenomena that cast doubt on what we thought we knew about the universe's structure. These pioneering studies are reshaping our comprehension of the cosmos, sparking renewed interest among cosmologists globally. These findings prompt a critical question: could our long-held cosmological beliefs be fundamentally incorrect? Are we on the cusp of a paradigm shift that will alter our perception of the universe? In this video, we explore the groundbreaking theories that the James Webb Space Telescope has recently disproven. As the foremost observatory for the coming decade, the James Webb Space Telescope serves a global community of astronomers. It delves into every phase of cosmic history, from the universe's initial luminous moments following the Big Bang to the formation of solar systems capable of supporting life. The James Webb Space Telescope represents a monumental leap in our comprehension of the universe and our origins. Building upon the legacy of the Hubble Space Telescope, James Webb stands as a state-of-the-art observatory, featuring a massive 6.5-meter main mirror designed for infrared astronomy. Its primary mission is to peer deeper into space, capturing the earliest stars and galaxies, and to probe nearby cosmic dust clouds to study the formation of planets and stars. Remarkably, the James Webb Telescope is nearly as large as a tennis court. It was ingeniously designed to fold like origami to fit inside its launch vehicle, later unfolding in space, akin to a transformer, to achieve its operational structure. Launched in late 2021, the James Webb Telescope is a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency. Its launch, on December 25, 2021, from French Guiana aboard an Ariane 5 rocket, was a landmark event. Orbiting the Sun at a distance of 1.5 million kilometers from Earth, the James Webb Telescope marks a thrilling new chapter in space exploration, particularly in our quest to understand life-supporting planets like Earth and the evolution of our solar system. The mission of the James Webb Space Telescope is to gaze back in time, observing the universe's earliest stars and galaxies. This endeavor aims to expand our understanding of the universe's origins. However, the deeper we delve into the vast cosmic mysteries, the more enigmatic puzzles we uncover about the cosmos. This has been exemplified by one of Webb's initial major discoveries, which was both exhilarating and perplexing. Webb revealed the existence of fully formed galaxies much earlier than what the widely accepted standard model of cosmology had anticipated. According to this model, which forms the basis of most cosmological studies, a specific sequence of events unfolded following the Big Bang. Initially, gravity clustered denser regions of cooling cosmic gas, leading to the formation of stars and black holes. These stars were then drawn together by gravity to form galaxies. Yet, the data from Webb suggests that, according to the standard model, some massive galaxies formed too quickly. This discrepancy is not minor. It's akin to a narrative where parents and their children appear at a time when the grandparents are still children themselves. And this isn't the only instance where such an anomaly has been observed. Recent discoveries by the James Webb Space Telescope have further challenged our understanding of the universe. A key example is the ongoing debate about the Hubble constant, which measures the rate at which the universe is expanding. Scientists are struggling to agree on a single value for this expansion rate, adding complexity to the puzzle. There are two primary methods for estimating the Hubble constant. The first involves measurements of the early universe, like those provided by Webb. The second method calculates distances between stars in the current cosmos. Despite decades of research, these two approaches consistently yield conflicting results. Scientists initially hoped this discrepancy would resolve as data became more accurate, but the issue has persisted, even with significantly improved data. In fact, recent findings from Webb have intensified this discrepancy. This persistent inconsistency suggests a fundamental issue with the standard model of cosmology, not with the data. The possibility of two major flaws in the standard model is alarming, considering the model has undergone numerous revisions over the past 50 years to align with the best available data. This situation is leading scientists and astronomers to suspect that there might be underlying elements in our cosmological understanding that need reevaluation. There's a growing sense among some researchers that we might need to reevaluate the standard framework of cosmology and perhaps rethink some of the most foundational aspects of our universe. The standard model of cosmology stands as a testament to human creativity, skillfully blending hard-earned empirical evidence with the abstract complexities of mathematical physics. Its origins can be traced back to Edwin Hubble's groundbreaking discovery in the 1920s that the universe is expanding, a pivotal piece of evidence supporting the Big Bang theory. Another landmark moment occurred in 1964 when radio astronomers detected the cosmic microwave background, or the residual radiation from the early moments of the universe's expansion. This discovery painted a picture of the early universe as a hot, dense soup of subatomic particles that has gradually cooled and become less dense over time. Over the past 60 years, cosmology has significantly honed its ability to explain known facts about the cosmos. However, to achieve this high level of precision, astrophysicists have often had to make adjustments and refinements to the model. In the current standard model of the universe, it's proposed that only about 4% consists of normal matter, which includes all living entities, planets, and everything else visible. The vast majority, comprising approximately 96%, is made up of unseen substances known as dark matter and dark energy, accounting for around 28% and 68% of the total, respectively. Another notable addition to the standard model is the concept of cosmic inflation. Developed in 1981 to address paradoxes in the earlier Big Bang theory, it suggests that the early universe underwent an exponential expansion for a brief moment immediately following the Big Bang. This hypothesis resolves certain issues, but also introduces new complexities. One of the more provocative implications of this theory is the possibility that our universe is just one among countless others. However, these other universes might be inherently undetectable, both in reality and in principle. The elements of the standard model, such as dark matter, dark energy, and cosmic inflation, are not inherently suspicious. It's not uncommon in science to rely on indirect evidence for phenomena that cannot be directly observed. This approach has been a cornerstone in advancing our understanding of the universe and its complexities. The recent unexpected data from the James Webb Space Telescope regarding galaxy formation, coupled with the growing discrepancies in the Hubble constant, naturally lead to questions about potential flaws or gaps in our current cosmological model. There's a familiar narrative in science that often serves to assuage these concerns. It goes like this: researchers develop what they believe to be a successful hypothesis, but as new data emerge, they find their theory is incorrect. This leads them back to the drawing board, where they formulate new ideas that better align their hypotheses with the facts. This process is seen as a testament to both scientific success and humility, and it's a story that scientists are often proud to tell. In the context of the challenges posed by the James Webb findings, cosmologists might simply need to identify a new dark entity or phenomenon to resolve these emerging conflicts and align our understanding of the cosmos with the latest evidence. However, there's another possibility that we might be at a juncture requiring a significant shift in our fundamental approach to understanding the universe. Such a change could compel us to reconsider the basic components of the universe and perhaps even rethink how we approach cosmological studies. Cosmology stands as a unique discipline within science, pushing scientists to address fundamental questions about the nature of the environment in which science itself operates. This includes exploring the essence of time, space, the consistency of scientific laws, and the role of observers in the act of observation. Due to its proximity to both science and philosophy, cosmology often finds itself grappling with the underlying assumptions that remain unseen yet are embedded in the tools and methods used. These assumptions might include the belief that scientific laws are immutable over time. However, it's precisely such assumptions that may need reevaluation to address discrepancies in the traditional cosmological model. One proposition, put forward by physicist Lee Smolin and philosopher Roberto Mengabira Unger, is that physical laws might evolve and change over time, with different laws potentially competing in effectiveness. An even more radical idea, proposed by physicist John Wheeler, suggests that every act of observation not only affects the future of the universe, but might also influence its past. This concept emerged from Wheeler's efforts to unravel the mysteries of quantum physics, leading him to contemplate a universe where observer participation is a fundamental component. In this concept of a participatory cosmos, every act of observation is viewed as a new act of creation. However, it's not immediately clear how such significant shifts in our scientific understanding could aid in deciphering the complex cosmological data currently perplexing us. Part of the challenge lies in the fact that the data we gather is often influenced by the theoretical assumptions of those collecting it. To step back and reevaluate such foundational principles of our knowledge would not only require a leap of faith, but could also lead to a revolutionary advancement in understanding. Historically, major scientific breakthroughs, such as Copernicus's heliocentrism, Darwin's theory of evolution, and Einstein's theory of relativity, have all had profound cultural impacts. These theories altered our perception of our place in the universe, questioned our unique distinction from other creatures, and challenged our basic understanding of time. Any similar breakthrough in modern science would likely have comparable effects on our self-understanding. According to philosophers and historians of science like Robert Crease, such paradigm shifts significantly influence our knowledge and perspective of ourselves and the world around us. They encourage us to reconsider what we accept as fundamental truths, potentially leading to a deeper and more comprehensive understanding of the cosmos. At Stony Brook University, where the intersection of science and philosophy is explored, it's acknowledged that philosophy plays a vital role, especially when further empirical research may not suffice to answer scientific questions. While it's not yet clear if a philosophical approach is what's needed to resolve the current cosmological quandaries, if continual modifications to existing theories prove inadequate, we might need to conceive a new narrative about the universe and find novel ways to express it. However, despite the vastness of the cosmos, the portion that is accessible and understandable to humans is limited. Even as the universe expands, encompassing countless galaxies, stars, planets, molecules, atoms, and subatomic particles, our capacity to analyze and understand it is bounded. This limitation stems from the finite number of particles, the amount of energy available in the universe, and thus the finite amount of information we can glean about our world. While we face these limitations in terms of accessible energy, observable particles, and measurable data, it doesn't imply that our quest for knowledge should cease, or that our efforts to learn all we can should be diminished. We must continue to push the boundaries of knowledge to their utmost extent. There's still a vast amount of science yet to be discovered, with many unknowns possibly being unraveled in the future. The current mysteries and challenges in cosmology may well be resolved as we persist in our exploration and understanding. While the future might unveil more about the cosmos, what we can know is inherently finite, suggesting that some aspects of the universe may forever remain beyond our grasp. The universe might be boundless, but our comprehension of it is not. Despite these limitations, the ongoing discoveries of the James Webb Space Telescope, JWST, continue to excite and inspire. In its first year of scientific operation, orbiting nearly 1.5 million kilometers from Earth, JWST has already achieved remarkable milestones. It completed its initial deep field campaign, turned its infrared optics to observe Mars and Jupiter, and captured spectra directly from an exoplanet's atmosphere. It has also managed to block out a star's light to study the debris disk orbiting it, detected its first exoplanet, and observed some of the earliest galaxies in the universe, those that existed at the cosmic dawn. Additionally, the James Webb Telescope has captured the most detailed and awe-inspiring images of iconic celestial objects. As it embarks on its second year of exploring the depths of space, JWST has already unveiled a wealth of cosmic beauty, showcasing wonders both near to our home and in the far reaches of the universe. The study of the cosmic era that began roughly 1 billion years after the Big Bang is a pivotal aspect of the James Webb Space Telescope's mission. This era, known as the Epoch of Reionization, marks a significant period when the first galaxies emerged. Their appearance caused the neutral hydrogen pervading the intergalactic medium, IgM, to reionize, thereby making the universe transparent. Studying this epoch is challenging due to the significant redshift and the presence of neutral hydrogen, which render it difficult to explore using visible light, making it the ultimate frontier for cosmic surveys. This period, often referred to as the Cosmic Dark Ages, is enigmatic due to its lack of observational clarity. To detect light from this era, astronomers rely on observing specific wavelengths, such as the 21 km transition line, which falls in the mid-infrared spectrum but is beyond the reach of current detectors, or the H-alpha emission line, which is in the radio spectrum. Recent breakthroughs have been made in this area. A global team led by the Caponi Astronomical Institute, KOI, successfully resolved the H-alpha emission line using data from the James Webb Telescope's MIRI instrument. This achievement marks the first confirmed identification of galaxies from the cosmic dawn. Looking ahead, astronomers, including those at Swinburne University, aim to push the boundaries even further in the telescope's second operational cycle, deepening our understanding of this pivotal period in cosmic history. Pykar Glasbrook from Swinburne University of Technology and an international team have been allocated 615 hours to conduct a significant survey using the James Webb Space Telescope, JWST. This project, known as the JWST Large Area 3D Parallel Survey, will utilize JWST's near-infrared imager and slitless spectrograph, NIRISS, to conduct pure parallel observations over 1,000 square arc-minutes. The expected outcome of this comprehensive study is to gather spectra and redshift data for approximately 60,000 galaxies spanning from the era of cosmic noon to the cosmic dawn, roughly 10 to 13 billion years ago. This period covers the emergence of the universe's first stars and galaxies to the birth of the second generation of stars, also known as population-sized stars. A redshift survey of this scale will allow astronomers to analyze 3D clustering during the epoch of cosmic growth, revealing the intricate relationship between dark matter halos and the accumulation of baryonic matter. Additionally, it aims to establish a benchmark set of stellar mass functions for well-defined spectroscopic samples. It will investigate the origins of galactic quenching, provide two-dimensional measurements of the abundance and age of galaxies, track the buildup of galaxies, and conduct a census of rare, high redshift bright galaxies and other unique objects across all redshifts. The size of the survey also opens up opportunities for data-driven discovery using modern machine learning techniques. These methods will be pivotal in uncovering novelties and anomalies within the vast cosmic dataset gathered by the JWST. Carl Glasbrook and his team, including P. Hakim Attic from the Institute of Astrophysics in Paris, are spearheading a project known as the Gravitational Lensing and NIRCom Imaging to probe early galaxy formation and sources of reionization, or GLIM-PSE. This observational campaign will utilize the NIRCom technology to examine low-mass galaxies that formed a few 100 million years after the Big Bang. By capturing ultra-deep images with the Webb's near-infrared camera, NIRCom During a 148-hour observation period, their goal is to delve into the processes that drive galaxy formation, such as gas accretion, star formation, and the feedback mechanisms that inhibit further star formation. Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q and a sessions with experts. Your membership will grant you the chance to participate in live Q and a sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment